So today we are going to talk about the electric motor selection and drive selection. So what is going to be the different motors that we can use for electric vehicle application, and what is the control strategy that we can apply? So there are so many control strategies in books, in papers, in different areas, but what is actually applied in an electric vehicle? That is what you people need to know, right? So we will concentrate on all these things, and we will understand what is the solid difference between all these motors and why particular motors are mostly used in most of the electric vehicle, and why some of the motors are still at research stage. We will understand all these things in the today's session, right? So the first thing that we have to understand before going into electric motor selection, you have to understand the vehicle target setting. Say whenever whenever you are working in an electric vehicle company, you imagine an electric vehicle company in your mind. Your boss will come and tell you, Prashant, today we are going to start a new project, and this project is nothing but our company is going to launch a new car. It is going to be a SUV car, a sports utility vehicle, right? So the SUV car. So our team has to develop a powertrain for this car. So my manager will be coming and telling me. So now what we have to do? Now what, as an engineer, where I have to start? That is where we are going to understand now. The first thing. So when you look at the vehicle and automobile development, we call it as the product development process in automobile. And the product development process is of different stages, basically. So the first stage, here is the stage where you, for example, you study the benchmarking. You do benchmarking. Means what? For example, who is the competitor for Mercedes-Benz? Can you people tell one or two examples? W, Audi, and these are all close competitors for Mercedes-Benz. Okay. And when I say Tata Motors, who is the close competitor for Tata Motors? Right? So the first stage, what happens is you identify the competitor. Say I am Maruti Suzuki. Okay. So what I will do, I will look at what Tata Motors is doing, what the other competitors are doing. Hyundai is doing. Hyundai is, for example, if in Hyundai there is some vehicle which is selling very large numbers, people are getting attracted to that vehicle. So immediately what will happen in Maruti, all the companies, they will discuss why that particular vehicle is selling a lot. What is the special nature in that vehicle? Whether the performance is better or the features given for the customers are better. What is that thing that makes that customers attracted to that particular vehicle? So they will start doing this activity. It is called benchmarking. So in a product development process, initially they do the benchmarking with the competitor. In some cases, they may not have a competitor, a very brand new vehicle. It's a new segment vehicle. In that case, they don't have a competitor. What they will do? They will go to customer. They will go to public and take the survey. They will ask the people, what do you want in a car? What do you want in an auto? What do you want in a two-wheeler? And based on the survey results, they generate the targets, the vehicle targets or the vehicle requirements, you can call, right? They decide what is the top speed that most of the customers are expecting. What is the acceleration that the most of the customers are expecting? What is the gradability? How much load they want that vehicle to take off. So all these inputs, they have to take it from the customer and put it in front of the group of engineers, and they will sit together and they will decide that this is what going to be the actual specification of this vehicle. And you know the Tata Ace, if you heard about the Tata Ace success, why Tata Ace is such a success in India? Because if you read the history of Tata Ace, the project started with, actually when the Tata Ace came, there was no such vehicle, there was no target, say for example, benchmarking vehicle at that time in India specifically. So they did a lot of survey. They started from Delhi and from Kashmir to Kanyakumari, they did a survey and they found that this is what Indians expect in terms of fuel economy, Indians expect in terms of acceleration, loading capability, gradability. All these factors we get and we put it in the initial full vehicle level conception. And after we decide the full vehicle level conception, then we go to the next levels, like module level. So once I decide the whole vehicle level targets, then I go for power component level, say for example, system level targets. What I will now tell, I will tell that this is the target for powertrain. This is the target for suspension. This is the target for steering. So like this, I will make a system level target. And after that, we make a component level target. So component level means, let us discuss about powertrain because that is our area of focus today. So inside powertrain, like it is a motor, it is the inverter. So what is the motor level target? So what is the total peak power that motor has to achieve? What is the peak torque that the motor has to achieve? What is the current that the motor has to consume? All these component level targets has to be taken, and they have to make it like component design should take place, and the component simulation will take place here, and then they will start testing the component level testing will happen, and then your module level testing will happen, and then the final vehicle level testing. All the systems together inside a vehicle, the vehicle level testing is going to happen. But however, you see that there are some companies in this world today now, they follow some unique approach. This is actually an established a very long, for a very long time, people have been using this V development process, automotive development process. Until now, they have been quite successful with this. But still, right now, there are some companies now looking at some other options of development processes. But understand that in this case, as our focus is on powertrain, so what happens is at this point of time, you have your component design and simulation. So the people design the motor, they design the motor components, they design the inverter components, they design all the e-drive components, and they simulate it and they check whether it is meeting the targets what we set. So for example, the targets could be like this. Say this is an example of Chevrolet Volt. I have taken the reference from Chevrolet Volt. You know, Chevrolet, right now we don't have this car. Right now we don't have this company in India, GM, General Motors. They flied out of our country because they are not able to compete with other competitors successfully. It's too much of competition in India on the car market. So, but this particular vehicle, Chevrolet Bolt, is one of the very successful electric vehicle in the market, in the European and the American market. And you can see that this vehicle, say for example, this vehicle was developed by compared this vehicle with the Spark. There was a vehicle called the Chevrolet Spark. You know, I think people might be knowing that. So they compared the vehicle characteristics with that vehicle, and they created the new vehicle. So the new vehicle has the target they set was old vehicle, the Spark vehicle, acceleration was 0 to 60 in 7.5 seconds. And the new vehicle they are designing, they kept a target of under 7. And the previous vehicle, the previous generation vehicle, it was like 28% gradability was there. But in the new vehicle, they want to increase that gradability. So means slope, it has to climb more degree of slope. So they increased to 30. And the previous vehicle, the range was only 82 miles. And the new vehicle they are developing, they set a target of 200 plus miles. So based on these are the vehicle level targets. Some of the example, there are so many vehicle level targets are there. These are few vehicle level targets. Say what is the weight? What is the weight target? What is the acceleration target? What is the gradability target? What is the range target? That is finally important. Today customers are asking, sir, give me a car with 1,000 kilometer mileage. Even some people are asking, sir, 1,000 is not enough. I want more than that. Right? There is no end for expectations of a customer. You know that especially in India, especially Indians, we Indians expect too much. Right? But still we will not give so much money for that. I think you people accept it. So 200 plus miles is what the target they have set for the vehicle. So what happens when I keep a target? This is a vehicle level target. This is a vehicle level target. So you have to convert vehicle level target. So now tell me, let us see. Can you people, any one of you tell me like what I expect? So if I want more range in a car, what I expect from a motor basically. What my motor should do or should not do. So end of the day, your motor's consumption of current, the power consumption should be lesser as possible. So when the motor consumes, the motor should consume lesser current. The motor should consume less amount of current, less amount of power. At the same time, it should meet all the expectations. So when the motor consumes less amount of power, I save power from my battery pack. And when I save my power from the battery pack, my battery pack will be able to provide me more and more range. So basically, this is what I expect in the range perspective, right? So similarly, for every requirements, every vehicle level requirements, there are some characteristic of the motor that should be noted down. Say for example, acceleration. So if you expect a car to travel from 0 to 100 km per hour within 2 seconds, what do you think that motor should be able to have? That capability, what capability the motor should be able to have? So when I need a 0 to 100 km per hour in just 2 seconds, what is needed is I have to develop torque, the maximum torque. So to develop a maximum torque, I have to supply a maximum current. So it is not just I am supplying maximum current. The motor and the motor components, the inverter and the inverter components should be able to withstand that maximum current. That is much important. So the ability of the motor components, the ability of the inverter components to withstand such a huge amount of current for a short span of time. That is what we need to have a better acceleration in a car. So these are all some of the motor level expectations, right? I hope people got a clear picture on this, right? So what happens is so that the vehicle level requirements like this are getting converted into motor level requirements. So like this, we transfer the vehicle level requirements into motor level, powertrain level and motor level requirements and inverter level requirements. I hope this slide was very clear for all the participants. So let's understand it on the drivetrain level. Let's understand this on the electric drive requirements level. So when you look at, so yesterday we have been seeing the torque power characteristic, torque speed characteristic of the electrical motor, and we see that initially the motor was giving a constant peak torque, and after the base speed the peak torque starts reducing. Okay, so but what happens here, when the motor develops a peak torque constantly, it develops a peak torque. What it means? It means that there is a high magnetic flux density that creates that high torque. So what I expect from, so when I'm starting my vehicle, I expect high torque, high starting torque and high acceleration. For that, what I need from a motor is a high magnetic flux density, so that it can consume, it can withstand huge current. So what we expect from the beginning of the motor operation is high magnetic flux density. And the second part, once my vehicle accelerated, what I need, once my vehicle, imagine your vehicle is now in a constant speed driving. Say for example, in this case, like when I expect high efficiency, once the base speed is crossed by your motor, then what do you expect from the motor is high efficiency. So to get high efficiency, what I need to avoid the losses inside the motor. I need to avoid the core losses. I need to avoid all the eddy current losses inside my motor, right? And similarly, when my vehicle enters into a highway region where I have a constant highway speed, what I expect at that time, my motor will be running at a very high speed. When my motor is running at a very high speed, say imagine 10,000 RPM, can you imagine how much centrifugal force will be exerted on the rotor when it is rotating at 10,000 RPM? So my material I am using in the motor should be able to withstand such a huge amount of force. So you told we will see that magnets will be placed on the rotors. Can you imagine 15,000 RPM, 20,000 RPM, if a rotor rotates, what will happen to the magnet? There are chances that the magnets can fly out or come out of the rotor. So what is the ability of the motor to withstand such a high speed? So these three are the very, very important requirement for a motor when we are selecting a motor and sizing a motor. So let's understand it more deeper. So when you look at E-drive, E-train, this is called as the E-axle. Yesterday I have shown you this multiple times. So this is what an E-axle mean. So what does an E-axle contain? Can you people list down to me? What does an E-axle contain? So when you look at the E-drive and E-axle, what is that E-axle? Expectations from an E-axle. High power density. So I told you yesterday that high power density. So the motor should be able to generate more power. At the same time, the motor size should not be very bigger. It should be very, very small. At the same time, torque density also same. It should be able to generate maximum torque and many more torque. But at the same time, the volume that the motor occupies should be lesser and lesser. And wide speed range, the motor should be able to run for a wide RPM range. Say from 0 RPM till 20,000 RPM, you should have a wide RPM range. When I have a wide RPM range, I told you yesterday what will get widened. Some spot, I told, some spot, that is the clue I'm giving. So when you have a wide speed range, the speed spot zone will increase, and because of that, you will have the engineers will have the freedom to operate the motor at a different speed regions where the motors are more efficient. So you need a good electric drive, a good electric motor for automobile application should have a wide speed range and high efficiency. Obviously, it's all dependent, and better NVH, that is also very, very important. The noise, vibration and harshness. So the motor I'm using in an automobile should not generate more noise, should not generate lot of vibration like an IC engine, should not behave harshly. If you say the IC engine, it will be very, it will create lot of vibration and it will create lot of noise. Some people love that noise and some people hate the noise. Okay. End of the day, for the society, it is a noise, right? So the noise, vibration and the harshness characteristics are also very important when we are selecting an E-drive for an automobile. And the reasonable cost. Behind all these things, one of the very important aspect is the cost. If the cost is not meeting the customer demand, then the product will not sell, right? So the cost is pretty much important, much important compared to all other parameters. And the reliability. So reliability means how long this motor can survive. So as I told yesterday, like the Tata Motors, the Tata Nexon, they launched recently. How many years the warranty they have given for Tata Motors, Tata Nexon? How many years warranty they have given for the Tata Electric Nexon, for the motors and battery? Any idea? So 10 years they have given, 10 years warranty they have given for the motor and the battery. Can you imagine how come such a high warranty, so many years? Have you seen any company giving 10 years warranty to an engine or any engine vehicle? In my lifetime, I have not seen. So in the Nexon, it is like a pure warranty on the motor and battery. And how this is possible? Because the motors naturally have the reliability nature. So basically, reliability means what is reliability? The motor should be able to function as per its design life. So if the motor is designed for 15 years, for the 15 years, the motor should work in the same way as it is designed for. That is called the reliability. So the reliability, in this case, the reliability of the motor, transmission, the inverter, everything is included when we are developing the E-axle. And the last two things are, the final one is the high intermittent overload capability. So this is happens, suddenly you will be overtaking, you will be going in a road and suddenly you will see, you will start overtaking a car and immediately you will see a front truck, a big truck coming in front of you. Within a fraction of seconds, two things will be there in mind. One is, if you overtake that vehicle, you will be safe. Otherwise, you will be heaven or hell, right? So we have to decide. So immediately, what we will do? Immediately, you shift down the gear, you jump on the accelerator, right? And immediately you accelerate the vehicle and to overtake the vehicle. So that is called a sudden intermittent overload. So you are applying intermittently, you are applying overload on the motor, and the motor should be designed for these cases also. That is what we call it as high intermittent overload capability. So that means suddenly the driver might jump on the accelerator. That means he might supply huge amount of current suddenly from the inverter. So the motor and the inverter components should be able to withstand such kind of huge amount of currents. Correct? So these kind of abilities are what required from an E-axle. Let us look at an E-axle in an exploded view. Let us explode it completely. Let's understand this. So this is what an actual E-axle is basically. Let's understand it component level. So what is inside an E-axle basically? So you have your motor. This is your motor where your motor housing is there, and you have the stator, you have your rotor, right? And this rotor is going to sit on certain bearings. We have the bearings on both the end of the rotor, right? So without bearings, it is not possible to rotate. So we need a bearing, and that too, they are all very special bearings. And since the bearings are very big, they are not very small, tiny bearings, they are very big bearings, because the load which will be acting. Basically, what is the purpose of using bearings, guys? Any mechanical engineers, can you people give 1 or 2 points on this? To reduce friction, okay, for the free rotation of the shaft, I would say. Yes. Second purpose is to separate the moving parts from the non-moving parts. So actually, say the bearings make sure that the shaft is properly aligned. That is also very important. Say if I have one bearing this side and another bearing that side, so you can see that. So what happens is this shaft should get aligned straight. If there is a misalignment, what will happen? It will damage the whole system inside. So the shaft should be completely balanced. It should be aligned properly. And more than that, more than all these things, this rotor, basically the rotor is very heavy component. And this rotor, when it is rotating, I told you, when it is rotating, it will be developing huge amount of forces, correct? So the forces which are developing, that load, the forces which are acting as a load, that load should be withstanded by the bearings also. So the bearings also withstand the load that is created by the shaft when it is rotating. But understand that an E-axle basically has your motor housing, your stator and your rotor, and you have the bearings. And since it is a bigger bearing, it need to have a proper mounting for the bearing. So we call it as bearing plates. And the bearing plates on the other side, you can see we also have a gearbox. You have the transmission system, either a single speed transmission, dual speed transmission. Sometimes this is an example of Audi e-tron. I have taken an example of Audi e-tron. So Audi e-tron uses an epicyclic gear train inside the transmission, right? It's like a epicyclic gear train in Toyota Prius, right? So in this case, they use an epicyclic gear train with a conventional gear transmission. In addition to that, they also mount the inverter very close to the motor. Why they are mounting the inverter part, power electronics inverter, very close to the motor to achieve what? The primary reason is actually to increase this thing, the power density and torque density. So end of the day, the whole E-drive should be occupying lesser space as possible. They should be as closer as possible. right? So when we make this, what happens is we bring the power electronic system very close together. And when we bring it close together, and actually, sir, what you told is, when I bring it more and more close together, there are also some problems possible because of EMI/EMC issues, right? So that is also some possibilities are there. We will discuss more in the coming slides, but understand that this is just to explain you what are all the components of an E-axle in quite detail. So basically, understand an inverter, a motor, and the motor housing. You have the stator, the rotor, and the bearings, the bearing plates. You have the transmission gear, and you have the differential output. And you can see this is the flange, the final flange shaft. And where it is connected to? It is to the wheels. Right. So in this case, actually, Audi e-tron has a dual motor concept. So it's like they use multiple. There are many models in the Audi e-tron. So, but this is one of the model, right? So in this case, directly the wheel output, you can see the flange output will be going from here, basically, right? So this is the drive shaft. Basically, it's a flange shaft, the drive shaft. So when I ask about e-drive, so if someone asks you what are all the components of an e-drive, this is what we can understand. In addition to that, what else we have in an e-axle drive system is we also have the sensing systems. Say, for example, the resolvers and encoders. What is the purpose of using resolvers and encoders in a motor housing? To sense what? The main component that rotates here is the rotor. Stator is not going to rotate. So the rotor's position is what is very primary for the positioning, and we use the resolvers and encoders to determine the rotor position, flux angle that is generated there. And when we classify, when we see that, there are so much of classifications of motors that are available in the market. So people call it a synchronous motor, asynchronous motor, and reluctance motors. But as I told you already that all these motors may not be suitable for automotive application, especially electric vehicle application. When you talk about electric vehicle applications, there are few motors that they are meeting the required targets or required demands of the electric motor. Some of them are these motors. The first one is the brushless DC motor, BLDC, and the second one is the PMSM, permanent magnet synchronous motor, and the third one is the induction motor, and the fourth one, the new member to the family, a surprising member to the family of motor, is the synchronous reluctance motor. So these four motors are right now dominating the whole traction market. Either it is starting from two-wheeler till a huge mining truck, right? Any one of these motors will be used. It is not something out of this motor. So either a brushless DC motor, PMSM, or an induction or a synchronous reluctance motor. Guys, this is different from SRM. Switched reluctance motor, that is different. Okay. Understand, this is synchronous reluctance motor. We will discuss about that in the coming slides. So these four are the major motors used in the electric vehicle application. So we will start understanding how does these four motors differ. And to make our work easier, or make the work of the manufacturer easier, today what happened is, what are the two main components of a motor? Stator and the rotor. So what happened is, now engineers, in order to make the electric drive more efficient, in order to make their designs more quick, what they have done is, they have made the stator component common for all these motors. All these motors here, what I'm showing, brushless DC motor, PMSM, induction motor, synchronous reluctance motor, all these four motors, right now, design engineers are using the same or almost identical stators, right? So because of this, what happens is, if we understand how one stator is being developed, we can understand the stator of all the four motors. And however, there is a small difference between a BLDC and a PMSM that we will make you understand in the coming slide. But understand that the stator has become a common thing for all the motors. So only difference is in the rotor side, and some of the differences are in the control side. That is what we are going to concentrate today. Initially, we will concentrate on the stator part. We will understand what is the difference that the stator gives, and we will understand the differences of the rotor in the other motors, and we will talk about the control part, right? Right now, this is the stator that we are going to discuss about. So when you look at the stator, this is what the stator housing, the stator carrier housing, and you can see the stator laminated core, and you have the insulation, right? And you have the copper windings, and you have our three-phase line coming from where? Where it is going to get connected to inverter. So the motor's three-phase power line is connected to the inverter. So when we look at a stator, say example, I have taken an example of a stator. So you have a stator and rotor. So when I remove the rotor, I can say this is how my stator will look like. And when I remove the windings, this is how my core will look like. So I have the insulation sleeves, These insulation sleeves are generally made up of special insulation materials, sometimes aramid paper. Nowadays people are using aramid paper, the special material. So basically, you know why insulation is done on a motor, right? So to prevent the losses, to prevent what do you say, end of the day, we should avoid the losses, the power loss from the motor. So you use the insulation sleeves inside the slot. And when I remove the sleeves, this is how it will look like, the stator core. And the stator cores are what? Stator cores are nothing but it is the thin laminated steel. So very thin laminated steel. So when you take the electric vehicle stator application, either it's the PMSM or any type of motor, the very important thing is the thickness of this steel. What do you think? What do you think the thickness of this steel will be? So currently in the electric vehicle domain, it is somewhere close to like 0.25 to 0.5 mm thickness. That is where the stacked lamination steel plate thickness is going. So that completely depends upon the manufacturing process technology, right? So today we are able to develop such a very thin material. At the same time, when I make a very, very thin material, what will happen? A thin sheet, what will happen to the strength? That's a question mark, right? So whether my material is having enough strength when I am creating such a thin material. So the materials what we use for these kind of stator core has become different for electric vehicle application, because your electric motors are like very they operate at very high temperatures, they operate at such a high pressure. So basically they should be able to stand that high the degree of forces that is generated there. So this is what the laminated steel will look like. And specifically when you look out the materials, these are the different materials that we use for the stator core. Either it can be a cobalt based iron ferrous, it is a cobalt composition with ferrous, or a nickel composition with ferrous, or silicon composition with ferrous. These are the special alloys that we focus on electric vehicle application, because you need more and more torque density, right? I told you why we need more flux density. Why we need flux density? Do you remember the graph I told you in the beginning? Any participant? So if I want more acceleration, I need to give more torque. To get more torque, I need to have more flux density in the motor. So I have to, my target is to achieve more and more flux density, right? That's how I use the different materials in the stator core, and I'll try to achieve more flux density, right? So when we look at the other aspects, so when we look at the stator, so currently we are looking at the stator part. So the other unique thing that in an electric vehicle, say whatever I am showing you here in all the slides, these are all some unique things that they need for electric vehicle. So the motors, we may there will be induction motor even in our home appliances also, but they are not the same as the induction motor what we use in an EV. That is what we have to understand, the differences between them. So when we look at the winding configuration, the stator winding configuration, there also exists a difference. So when you look at the winding configuration on the stator of an EV, so basically what people do is here they use something called as bar winding, right? So what happens is, like, we have different windings like concentrated winding and distributed winding. So here what happens is, when you look at the electric motor requirement of an electric vehicle, we need to achieve a high fill factor basically, and the end of the day, the manufacturing manufacturing process of the machine should be as simpler as possible. That is what the major requirement is. So looking at that, the concentrated windings offer very high fill factor. You can fill lot of more amount of current carrying conductors, and simple to manufacture. At the same time, thermal and electrical isolation, that is also better compared to the other windings. And when you look at, when you look at the structure, so overall, but because of this concentrated winding, what will happen is, we generally have, in a motor, we call it as two types of, the torque varies actually, right? So that reluctance torque which we demand, which is needed more, the reluctance torque is quite lesser, but when we use this type of winding. But however, in electric vehicle application, say maybe you can also tell it as like, bar winding versus standard coil winding. These are the winding construction. So when you use bar winding, this winding is what used in the electric vehicle motors. So bar winding motors have very high slot fill factor and they have very short end turn. So because of the short end turn, what will happen? You can reduce the stator's total length. You know, right? Stator's total length, the total motor's length can be reduced when you use this bar winding technique. So overall, what will happen? Your motor, size of the motor will be able to, will be smaller and better packaging is possible when we use the bar winding system. And at the same time, when we have such a bar winding system, they exhibit a very good performance, especially in transient conditions. Transient conditions means what you mean? Sudden acceleration. So suddenly you are giving some huge amount of current. And such kind of demanding transient conditions are there in electric vehicles, and that kind of conditions, your bar windings have very good, better performance. But still, there are some negative points on the bar winding also. Whereas on the negative skin effects, we call it as, like, there are some losses when the motor is running at very higher speeds. It's negligible, you can say. There are two categories we are using. One is the hub motor, right? This is how the hub motor will look like. And this is what we call it as mid-drive motor. So hub motor is directly fitted to the wheels. And why? What is the reason? Could any participant tell me why we use hub motor and where we can use hub motors? So when we talk about BLDC, the BLDC motor, the problem is basically this motor is actually working on a 6-step control. And because of the 6-step control, we basically have a very bad amount of torque ripple, right? So because of that issue, BLDC is not a good solution for all type of application. The very first thing you have to understand, because of its control methodology, the BLDC motors will not operate without torque ripple. So the torque will not be properly output from the motor, and because of this application, because of this, BLDC motors are limited to small applications like two-wheeler and three-wheeler applications. And even in two-wheeler and three-wheeler application, depending upon how much space you have in your vehicle, depending upon what is the space available in your vehicle, say compared to a two-wheeler and three-wheeler has more space, correct? But in case of a two-wheeler has very limited space. So when I have a limited space, I have, the problem of keeping the motor and putting a chain drive or a belt drive, whatever be the drive, I have to connect it to the wheel, right? So that is where these hub motors are giving advantage. And that advantage is only up to certain power, certain kilowatt of power. BLDC motors are not a right selection above certain power limit, especially above 5 to 7 kilowatt. So once your motor crosses 5 kilowatt, if you select hub motor, that may not be the right decision. What happens is, hub motor, there are many negative points. One is, it adds weight on the wheel itself. Say in a vehicle, we have something called sprung mass, unsprung mass. So this hub motor increases the weight of the wheel. Actually, it increases the unsprung mass of the wheel. So what happens is, you have so much of weight on the wheel. That is one negative point. Second thing is serviceability. When you have any problem on this motor, especially the problem will come only in the bearing side, right? And you can see that the bearing life has to be very, very higher. Otherwise, if the bearing fails, you will not be able to easily service these hub motors. That is also one of the reasons that people don't go for hub motors in higher power vehicles, and whenever they expect more serviceability. And if you put a hub motor, then that hub motor should be having very high serviceability. That means the life of the motor should be very high, and the motor component should be very high. That at the same time, whenever there's a repair, that it should be easy to service. And one more reason is the space availability. As I told, whenever you have a very limited space, then people go for, especially they go for hub motors, right? And moreover, in addition to that hub motor, we have the mid-drive motor. So in this case, this motor is kept somewhere in the vehicle, and from there you connect some belt drive or a chain drive or some gear drive directly to the wheel, and you drive the vehicle. That is what we call it as mid-drive vehicle. So BLDCs can come under the two category, and basically mid-drives are used wherever you have higher kilowatt requirement. More than say 4 or 5 kilowatt, people definitely go for mid-drive system. And moreover, you can see the scooter segment today in the market. Scooter segments, only low power scooter, little bit low power scooters, they go for hub motor. And if there are some markets, some people I am seeing that in the high power segment also they are using the hub motors, but still their serviceability problems are there. If you are purchasing such motor, there might be some problem. You have to inquire that, because hub motors have very big problem on the serviceability. I have known that the last 5 years, whoever bought electric scooter with hub motor are facing trouble with the hub. They are facing trouble with replacement of the bearing. They are facing trouble with repairing the motors. Right? You can check, you can inquire from the market as well. So, but depending upon, if your power capacity is low, then you can choose this hub motors, depending upon further other requirements as well. But as I told you, BLDC motors operate with the 6-step control, and because of that, what happens is you generate lot of torque ripple, and which makes it not a suitable candidate for high speed applications. So when you have a demanding application, when you have a higher power application, you should go for PMSM compared to BLDC. I would say, if you want a magnet based motor, in that case, if your application is high speed, then people go for PMSM, right? Compared to a BLDC, because the torque ripple issues can be avoided in the PMSM. So when you look at the BLDC motor system, so basically what happens is this BLDC is operating mainly based on the input provided by the sensors. So we have some Hall sensors, and especially one more difference between BLDC motor with other motor is that BLDC motor use 3-point sensor technique. You need to provide 3 sensors at different positions, and all the 3 sensors, Hall sensors basically. I believe you people know what is going to be a Hall sensor. I don't want to go deeper into that area. So Hall sensors gives the input signal to the controller, and based upon the position of the rotor, so based on the input from the sensors, the controller decides what is the IGBT, what is the switch, either the MOSFET or IGBT, whatever be the semiconductor switch, which switch should open. So for example, this is an example of a BLDC motor. This is the stator part, this is the rotor part. And you know hub motors are basically coming under the category of external rotor. External rotor. This case, this is an example of a hub motor, right? So this means, in this case, the outer one is the rotor, inner one is the stator, correct? But in this case, outer one is the stator, inner one is the rotor. I hope people understand the difference. In this case, the whole wheel rim is itself acting as the rotor part. So what happens is, this part is fixed. This part is fixed. So what happens is this part will rotate. That is why your wheel rotates. So the external rotor concept is called as the BLDC, the hub motor. Internal rotor concept is called as the mid-drive motor. The rotor position itself different. So from here you can understand this is an external rotor concept. So magnets are positioned on the surface of the rotor, and you can see that they are meeting the stators at this point here. And you can see this example. You can see this example that when you operate, when the motor is operating, these are the MOSFET switches, or you can say the IGBT is what you can call, either a MOSFET or IGBT depending upon the power requirements and temperature requirements. We use the switching devices basically, right? So these are the 6 switching devices, A, B, C. You have 2 switching devices. You can see that these are the switching devices, 1, 2, 3, 4, 5, 6. So what I need to do is, depending upon the signal I'm getting from the sensor, I am detecting the position of my rotor, right? Whether my rotor is in this position or this position or this or this. So where it is aligned with, I determine that with the help of my Hall sensor. And after determining that value, what I do, I will switch on the next switch to move the position from this to this and from this to this. So like this, the rotor keeps on rotating, following up the positions. So this is a 6-step, 1, 2, 3, 4, 5, 6. 6-step control, what we call. And because of this 6-step control, what happens is, between one commutation to other commutation, there is a small ripple. There is a small ripple always be there. And because of that ripple, whenever you expect higher speed performance, you will not get it properly. Stable high speed performance is not possible with BLDC motors. So end of the day, if you summarize the BLDC motors, you will have a very good power density. That means the torque density, power density is good initially. For a certain sizing, so for a certain level of motor power, the power output per frame size is higher. And one more difference is it uses a trapezoidal commutation, whereas in PMSM motor, it uses a sinusoidal commutation. So because of the trapezoidal commutation, the control is very easy. It is not like as complicated as PMSM. The control is quite easy in BLDC. These are all the reasons that people go for BLDC motors in two-wheeler. because the control is very easy to do and efficiency is quite good compared to the other motors. Efficiency is quite good. And what happens is the cooling system, especially the cooling system, in case the BLDCs have the tendency to cool very easily compared to the PMSM motor. Through convection and convection itself, they can cool very easily. But in terms of hub motors, temperature issues are there more. That is also one reason people go for a mid-drive motor. When the power capacity is more, when your motor power is more, then temperature generation will be more. So the temperature is more, then there are more problems that could come inside the motor. Losses will be more. So that is why people, whenever the power capacity is low, they select a hub motor. Whenever higher powers are there, then they go for the mid-drive motor, as I mentioned. So based on this point, the negative points are like more torque ripple compared to the PMS motors. And as you understand that the what happens is flux density is not very uniform. So here, because of this different control methodology compared to the other motor, your flux density will not be uniform in the air gap. And so when we look at this mid-drive motor, you can see the specification that kindly please look at the specification chart. You can see this is an example I have taken from one of the manufacturer. When we select a motor, especially the BLDC motor, you can see in this case it is a mid-drive motor. This is an example of a mid-drive motor, and you can see this when you select the motor, the parameters that we have to look at is the rated voltage, the rated power of the motor, and the total peak power. So peak power is very also important, and the peak torque that the motor can provide, and the torque at the peak power. So what will be the torque and what will be the RPM of the motor, and what is the peak efficiency of the motor, and what is the battery current it will consume continuously and during peak. So what is the difference, guys? What is the difference between continuous current and the peak battery current, where it is consumed? So when I am starting my vehicle, during the starting time, during my starting acceleration time, that's where I will have a very huge current flow from the battery, from my battery to my motor, right through the inverter. So that peak current that will only last, that can only last for few seconds. So the motors and the inverters, though the control systems, controllers, they have the ability to withstand this peak current only for few seconds. Whereas the continuous current, say for example 43 ampere they mentioned for this motor, this 43 ampere is continuously can be fed to this motor, right? And similarly, look at this motor. This is a hub motor. Can you see the difference? I told you very clearly why BLDC, where BLDC hub motor is used and where mid drive is used. Can you see the difference? Look at this area where I am circulating, the rated power output of the motor. So what happens is, so when you look at the hub motor, they are mostly suitable for the low power applications. So as you can see that this particular vehicle, the maximum speed was 43 km/h only. That was the maximum speed requirement, right? So in this case, they were able to use this motor power, this motor BLDC motor application for the in-wheel. We call it as the hub motor basically. So this is the mid-drive motor which is connected to the wheel using a belt drive or a chain drive. And you can see this is the hub motor, which is the wheel itself directly, right? So this is the specification. So as I mentioned, these BLDC motors are having a very less lot of limitations in terms of its operation, and because of that, it is only limited to only few applications, low power applications. And when you compare the PMSM motor, when you talk about the PMSM motor, let's compare it with the BLDC and PMSM. What are the differences basically? So when you look at the PMSM, it is having the sinusoidal distribution of the air gap, and because of that, you also have that winding. The winding is actually a distributed arrangement of winding, whereas the BLDC has a concentrated arrangement of winding with trapezoidal distribution. So here in PMSM motor, the control system is quite sophisticated, whereas in BLDC, the control is very, very simple, as I mentioned. And in PMSM, like in your BLDC, you need a Hall position sensor is enough. But in PMSM motor, you need to have a proper encoder, which should have a very high accuracy. That means the position of the rotor, is very, very important. The flux angle is very, very important, and that should be determined with a very high accurate encoder. That is why PMSM motors are very costlier. And because of all this reason, PMSM motors are performing better at higher speeds compared to BLDC. Both the motors are exactly the same, almost exactly the same in terms of usage, in terms of operation. The common thing is they both use magnets. The difference is their windings. So here it is a distributed arrangement of stator winding. Here it is a concentrated arrangement of stator winding. So we call it a sinusoidal distribution. And in BLDC we call it as trapezoidal distribution. Because of that, it is limited to only low power and low speed applications, whereas this is applicable for high speed applications. So as I told, the stator remains common for all the motors. Look at the rotor of a permanent magnet synchronous motor, PMSM motor. So when you look at the rotor of the PMSM motor, this is how it will look like. The rotor contains these are the permanent magnets embedded onto the rotor. And you people know, if you people are from electrical, you might be aware that we have two axes on a rotor. So one is the direct axis, one is the quadrature axis, so D axis, Q axis, right? So we have these two axes where the current flow takes place. So what happens is, in a PMSM motor, we have the permanent magnet embedded onto the motor. So because of the permanent magnet here, so here the rotor gives the force generated because of the permanent magnet, and on the stator side it is the electromagnetic force. So when you look at the permanent magnets, embedded on this motor, so the permanent magnets, there are many different types are there, like aluminum, nickel, cobalt, ceramic type, and neodymium, ferrous, neodymium series, we call it as a cobalt series. These are the different types of permanent magnets, and most of these magnets are like rare earth materials. They use rare earth materials. Because of that, there's a huge scarcity available in the market. Because of that, this permanent magnets price is very, very higher. It is fluctuating. And when we are designing the permanent magnets for the PMSM motor, the rotor design, we have to make sure that we select the proper magnet, right? So look at these examples. These are some of the development activities done by Department of Energy. You can see that these are on the Oak Ridge, it is on the ORN laboratory in USA. You can see that, say for example, 2004, the Toyota Prius. So in 2004, the Toyota Prius motor was looking like this. And 2017, you can see the stator's design. Not only the stator, rotor design. You can look at the rotor design change from 2004 to 2010 and 2017, how it has changed. And especially on the inverter part, 2004, the inverter was able to handle 35 kilowatt of power for 1 mm square of unit of area. The silicon carbide, the silicon IGBT they used, that can handle only 35 kilowatt per mm square. But 2010, Toyota Prius improved their motor technology, that they were able to achieve 45 kilowatt per mm square. And 2017, it was further enhanced that their inverters and system can handle up to 55 kilowatt per mm square. So every year and year, the developments are going on that they are able to have more and more power density. So the PMSM motors are widely and here also you can see. What do you people understand, guys? Looking at this picture, what do you understand, guys? This is the previous generation motor efficiency map. This is the new generation efficiency map. Can you understand what is the difference between these two efficiency maps? Do you remember something I told? I think twice I have told it. Because of all these changes, because of the position of the rotor, the design of the rotor, design change the rotor done, and the design change in the stator, design change on the inverter side, design change on the motor leads, they were able to expand the high efficiency region of the motor, the sweet spot region, what we were calling. So that sweet spot region got expanded compared to the previous generation motors, right? And you can see that similar example, especially these PMSM motors are widely used in the passenger car segment. So why, especially if you take, this is an example of Nissan Leaf. So Nissan Leaf, they used in 2013 also, they were using PMSM motors only, but they redesigned their PMSM motor by 2018 and they were able to achieve, can you see how much acceleration they were able to achieve? So they were able to improve their acceleration capability compared to their previous generation. Not only acceleration capability, their torque ripple, the torque ripple nature was also been stabilized more compared to the previous generation motors. At the same time, you can see that the previous generation motor was weighing somewhere 15.3 kilogram, whereas the new generation PMSM motor they designed, it was just 11.4 kilogram. And look at the current value. Look at the current value. The previous generation PMSM motor, what developed by Nissan, was able to only handle 356 ampere of current, whereas the new generation was able to handle 456 ampere current. Because of this, as the current increased, the torque capability of the motor also got increased. It went to 320 Newton meter. 320 Newton meter. But still, see, what is the magic the engineers have done? So keeping the same weight of the motor from 2013 to 2018, they were able to achieve higher torque, higher current capability, and lesser weight, right? On the motor side, on the inverter side also, they have reduced the weight. So this is what our engineers are working on, right? Behind the scene, the companies are working hardly to reduce these, to improve the motors and their characteristics. And when you look at the PMSM motor, as I told that we use the permanent magnets. So now the question is, how are to avoid the permanent magnets? Two things you can do. Either you completely avoid the permanent magnet, or you reduce the permanent magnet as much as possible. So Nissan implemented the second one. They don't want to completely go out of PMSM motor, but what they are doing is they implemented a technical system, technology. We basically call it as in our mechanical engineers, maybe mechanical engineers, you might be knowing grain boundaries. So using special manufacturing methodology, the magnets are being manufactured such a way that they are using very little amount of dysprosium. So the dysprosium is the material that they use, the rare earth material that they use in the permanent magnets. So the amount of dysprosium has been reduced further and further. Say 2011 Nissan Leaf was having this much, for example, this much permanent magnet, and 2018 70% of the permanent magnet was reduced on the PMSM motor. Because of doing all these things, that they were able to bring up more and more performance on the PMSM motor, right? And not only the change in permanent magnet, even the stator design change also happened. They have changed the teeth, stator teeth length. I will show that in the next slides. So because of that, they reduced the weight of the motor by nearly 4 kilograms. So the design modifications, when you take the stator, it is same. It is same for all the motors. The rotor side, that is the permanent magnet. This rotor looks like this on the permanent magnet. Let me come to the slide. So when you look at overall picture, when you compare the PMSM motor with other types of motor, PMSM is currently the widely used motor in the electric vehicle application, right? It is the widely used motor in the application. Because what is the reason? Because PMSM motor gives a fantastic power density. It gives a fantastic higher efficiency, very highly efficient. Currently, the PMSM motors are giving efficiency close to 95 to 97%. That is also one of the reasons that it is very attractive for passenger car market, PMSM motors. And one more thing is, compared to the other induction motor and other counterparts, it is quite easier to cool compared to the other parts. But still temperature issues are there in PMSM motor because of the permanent magnet. And high reliability. Manufacturing wise, yes, it is better compared to technologies like synchronous reluctance motor, switched reluctance motor. Manufacturing wise, it is actually good, especially compared to synchronous reluctance motor. And moreover, the very important thing is dynamic response. So the motor should be able to respond immediately when the driver presses the accelerator. So the dynamic response characteristic is available with the PMSM motor, which is not available with the BLDC. Here is where BLDC and PMSM changes. The dynamic response. So how quick the motor is able to meet the expect torque and power. Because here you can see that on the rotor side, we don't have any windings, right? We don't have any windings on the rotor side, because of which you don't have the copper losses on the rotor side. So you have better dynamic performance. And the negative side, yes, PMSM motor also has negative side. Say one is the main negative side is the rare earth materials on the permanent magnets. So because of that, the price of the permanent magnet motors PMSM motors are very higher. Compared to BLDC, it is very higher. And when I'm operating at very high speed means these motors can operate at high speed, but the very high speed, what I mean is like more than 15-20,000 RPM. At such a very high temperature, there are chances that the magnets can fly out, right? So the mechanical integrity is one of the issue that is there with the PMSM motor compared to induction motor. Induction motor, we don't have the permanent magnets. So we don't need to worry about very higher RPM. So higher RPM, there is no permanent magnet to fly out basically. So in PMSM motor, we need to worry about it, especially when you mount the permanent magnets on the surface of the rotor. And final thing is, as I told already previously, temperature. So when I go for very high temperature operations, as I told, PMSM motors, basically, they are suitable for passenger car application. And you know, passenger cars, they operate at very high speeds. Say, in the range of 7,000, 10,000 RPM, 15,000 RPM. So when the motor operates at such a high speed, until if you are not giving a proper thermal management or proper cooling system design in the motor, your motor will you can expect demagnetization will happen in the motor. And because of that, overall performance of your motor will get affected. So the PMSM motors are a very good candidate for high speed applications. So passenger car segment, high power segment, these areas you can take the PMSM motor, but at the same time your price, everything will increase because the control is very sophisticated. Machines, more and more permanent magnets, so cost of that also will be more. And when you look at, I told you very clearly, the change is only happening on the rotor side. And similarly, when you look at the induction motor, the common thing is the same PMSM, the same stator can be used in induction motor also. The same stator, what I use in an induction PMSM motor can be used in an induction motor also. So when I open an induction motor, so I have the rotor and I have the cage, the squirrel cage, what we call, based on our textbook knowledge, the squirrel cage and with shorted ends. But today the modern motor, the modern rotor is not looking like this, which we see in your textbook. This is what the rotor of an induction motor looks like currently. So this is the rotor that is used in the Audi e-tron. It is an induction motor rotor. Do you believe that it is a squirrel cage motor? Does it look like this, guys? I believe in your textbooks, you might be seeing squirrel cage motors like this only, even today. I'm not an electrical student, but I think, is it so or not? Yes. So in that, but if you see the latest manufacturing technology, it is not so. We are not having the squirrel cage looking like the same squirrel cage. So the design, there are a lot of design changes happened, especially because of the pressure in the automotive industry. So there is that necessity is the mother of invention. So there was a necessity. There is a necessity among all the automotive companies that they have to develop a motor which meets all the demands without magnet. That is why the induction motor has become a very important role. And the moment Tesla started using induction motor, there is a big speculation among the market. Why this guy is only using induction motor? Actually, the reason why he used induction motor is very simple thing. You don't think very high technically. The person who was recruited as a design engineer, the person who was recruited initially for the Tesla team, he was the design engineer for the General Motors EV1. There was a vehicle called General Motors EV1. There is an electric vehicle with induction motor. So that engineer who worked in the General Motors EV1 vehicle was recruited by Tesla, and so he told, sir, the induction motors can do much better. And he asked for a chance to prove that, and he proved it. And he proved to the world that yes, induction motors can also give the dynamic response that we expect, right? So the changes is majorly on here what happens is we don't use any magnets, we don't use any permanent magnets, we don't use any windings. So what happens is basically they use very thin laminated steel sheets on the rotor side. And let me go deeper. When we look at the differences that these motors has brought up compared to the PMSM, let's understand that. The induction motor system, basically, it eliminates complete elimination of all the rotor magnets, avoiding one of the highest machine cost contributor, right or not? So it contributes to save your cost. It saves your cost of your motor when you use induction motor. So these are all the reasons that Tesla says why we use induction motor. The rotor losses can be significantly reduced by adopting copper squirrel cage instead of aluminum. And the drive cycle efficiency of well-designed induction motor can challenge that of an interior permanent magnet motor also. It is very, very closer, guys. Compared to an induction motor and PMSM, it is a marginal difference. It is the margin difference that PMSM scores higher. So Tesla, what they are doing in Tesla, they are trying to bridge that gap, that difference. That is what they are trying to build up. Right now, yes, PMSM motors are a step ahead of the induction motors. So magnetic field strength in the machine can be lowered via the stator current to reduce the losses under light load. So basically, induction motors are very good at park load efficiency. Park load efficiency. Say whenever you talk about a powertrain system, we call it as low load, park load, full load. Three conditions are there. Low power, the initial condition, that is called low load condition, and then the park load condition, and then the peak power condition, right? So in the induction motors, they are very good at park load condition. The park load efficiency is actually better than PMSM. That means, to explain you what is the park load efficiency, let me show the graph which I told you, which I've shown you in the beginning of the presentation. This one. Hope you remember this thing. So this is the region. This is the region where your induction motors are very, very highly efficient. That is the reason, the main reason that some of the companies are still supporting induction motor, and obviously they are growing a lot. So this is the region where the induction motors achieves its very high efficiency, and it competes with PMSM. It competes with PMSM at this region. And what happens is, because of the absence of magnet, there is no problem. You don't need to worry about high speed operation. Correct? Because if it is the PMSM motor, I need to worry about it, because when my motor runs at very high speed, there are chances that the magnets can get flied out, or there are chances that the magnets can get damaged, you can say, or get stressed. So when in an induction motor, since I don't have magnets, I don't need to worry about the high speed operation. So the induction motors can do a fantastic job when they are running at high speed. That is why you can see the Tesla motors, what they use in the Model S, the latest Model 3 and Model S, all these motors are having capability to run up to 18,000 RPM. They don't worry about the speed. But if it is a PMSM motor, yes, definitely I have to worry a lot, because that is having an impact on the permanent magnet. So these are all the reasons that you see that induction motor is a very strong contender compared to PMSM. And when you talk about disadvantage, yes, some areas where PMSM is ahead. One of the reason is the losses generated by the rotor, because both the stator and the rotor have a lot of iron core. So because of the lot of presence of iron core, here you can see that the losses will be there. And overall, you say, like efficiency wise, efficiency is not stable. You can say efficiency is not higher at all operating conditions. That is also one problem in induction motor. So as I told you, the park load efficiency is very, very good, but maybe the initial time and when the high speed performances, efficiency may not be very good, stable compared to the PMSM motor. And especially, say, as an electric vehicle, we need everything. We need efficiency to be good at all the regions of the operation. And one more thing is the constant power speed region that I have shown in the graph, right? Some region. That constant power speed region is not very wide. That is also one reason. The sweet spot region where the motors can operate, the speed region where the motor can provide more constant power, that region is actually limited compared to the permanent magnet motors, PMSM motors. So what happens is, because of that, when you have a induction motor, you don't have the freedom to operate in a wide range. That is one problem. That is why right now Tesla is using other motor. What is the other motor they are using? Addition to induction motor. What is the other motor that Tesla uses in the Model S and Model 3 in some of their models? Any guess? Actually, the answer is permanent magnet assisted synchronous reluctance motor. That is the full name we have to call. And why this Tesla is getting such a big value in this company? Because this company works on area where people are not thinking about. That's the synchronous reluctance motor. The synchronous reluctance motor, when you talk about synchronous reluctance motor, what happens is people stopped using the synchronous reluctance motor because of the saliency ratio. So there is a term called saliency ratio, where the inductance between the stator and the inductance of the rotor, the ratio between these two, we call it as the saliency ratio. We need to achieve higher saliency ratio. But because in the synchronous reluctance motor, the design is in such a way that we were not able to achieve the higher saliency ratio. Because of that particular reason, that most of the traction application, they were not useful. However, if you see last 2-3 years, in industries, now these motors are replacing induction motors also, some of the areas. They are very highly efficient and they consume very less power compared to induction motors. They consume very less power compared to induction motor, very highly efficient, because there is no winding in this motor, synchronous reluctance motor. So in this case, the synchronous reluctance motor, the advantage is I don't use any windings. Since there is no, because of the windings, absence of the windings, what happens is I give lot of advantage, but the main problem is the saliency ratio. Because of that, I am not able to develop the required torque that is needed for an electric vehicle. This is what people were telling. People were blaming like this. And what Tesla did? What Tesla did? They used permanent magnet inside the rotor. I'll come to this slide later. So they used permanent magnets. Say on the state rotor side, they embedded the permanent magnet, and Tesla calls it as permanent magnet assisted synchronous reluctance motor. So the problem was solved. People were telling that synchronous reluctance motor can never be used in electric vehicle, and these guys have proved that no, it can be used. It can be used. And what they have done in the Tesla Model S, especially in 2-3 models, front wheel is driven by this motor, synchronous reluctance motor, and the rear wheel is driven by induction motor. So what they do you remember what I told about hybrid vehicle? Do you know what is the advantage of hybrid vehicle I told? Do you remember it, guys? What is the advantage of using hybrid vehicle? What we do is we run the engine at the most efficient region. I told, do you remember everyone? Yes, and they run the motor at the most efficient region. Because of running the two power plant at their most efficient region, the overall efficiency, the overall power consumption of the vehicle was reduced. Same way, same thing is applied here. Front wheel, they fixed permanent magnet synchronous reluctance motor, which is very, very highly efficient compared to induction motor. And the rear wheel, they placed the induction motor, which is very, very fantastic motor in terms of park load efficiency. So what they did now, they combined both the efficiencies. Overall, you can see the efficiency of these machines. Overall, the power consumption of overall power consumption. In addition to that, what they did, the inverter technology. They used silicon carbide MOSFETs, silicon carbide in the power electronic systems. Because of that combination of the silicon carbide with permanent magnet synchronous motor and induction motor, this combination is what making Model S and Model 3 successful in the market, right? So this is a very fantastic motor compared to switched reluctance motor. The synchronous reluctance motor have lesser problems, I would say, compared to SRM, the switched reluctance motor. But yes, still there are a lot of researchers working day and night. They are working on the switched reluctance motor also, because that is also a magnetless motor. But basically, right now Tesla came to know, and Tesla understood that without magnet, at least a very small amount of magnet has to be used. But could you tell me which is better? Say Tesla could have gone to PMSM motor. What do you think about the decision taken by Tesla? They went to synchronous reluctance motor instead of permanent magnet synchronous motor, PMSM, where it is full of permanent magnet. What do you think, whether the decision was right or not? To reduce the permanent magnet usage as much as possible. They don't want to completely come out of it. At the same time, see, they are keeping their induction motor where they started their journey. It is still there with them. At the same time, they are adding this additional motor technologies wherever required, like Toyota. So Toyota, how it uses multiple motors and one engine. Similarly, in their Prius, Tesla uses the combination of the multiple motors. So they run the different motors at their different higher efficiency regions. So this synchronous reluctance motor, they do not require field windings. They do not need expensive PM material if it is only synchronous reluctance motor. But what Tesla using is different. That is PM assisted synchronous reluctance motor. Very small amount of permanent magnet is used. But if I say that I should not use permanent magnet, without using permanent magnet, how can I meet the torque capability? Okay, let me tell the answer. So if I don't want to use the permanent magnet, then what I have to do is, in the synchronous reluctance motor, the rotor design has to be modified. You can see totally 3 barriers are there here. 1 through 3. For the flux to flow, there are 3 barriers here. And look at this picture. This is a rotor designed by a researcher in Australia, which is having somewhere close to, these are all the barriers. Can you imagine? This much of barriers are being designed on the rotor. Can you imagine? Here only 3, but here it is like multiple barriers are there. The problem is this kind of rotor is not so easy to manufacture. Because of that only, Tesla went to magnet assisted reluctance, because see, I need to create reluctance torque here. To create reluctance torque, I need to have more barriers here, and this is one way that you can do that, but this is not possible at this point of time. At this point of time, at this point of 2020, we don't have a very sophisticated, we don't have a very big technology, better technology to manufacture these kind of barriers very easily. That is why right now they have gone for the PM assisted motor. And once Tesla finds a way without way to increase these barriers, then they will completely remove the permanent magnets in the rotor side and they will keep it like this. You don't need any sort of permanent magnets inside that motor. So the synchronous reluctance motor, the problem is in their construction part and their manufacturing part. So I believe these problems will take a lot of time to, it will take time to reach a stage where your manufacturing capability is able to be done. That is all about the 3-4 motors, guys. I've briefed about, a little bit brief on the 4 motors and their plus and minus. So basically, every manufacturer, most of the manufacturer right now, 90% of the electric vehicle manufacturers are using permanent magnet synchronous motors only for the vehicle, electric cars and bus applications also. And very few companies, they use induction motor. Say Audi is using induction motor. Even Audi was using PMSM. Later they went to induction motor. And Tesla is using induction motor and the synchronous reluctance motor. They are new joining. So like this, new technologies are coming inside the motor side. So next part is on the control part. We know motor is working, but to run the motor, I need to supply current. So when you look at motor, so we have to supply some voltage and current to the motor. So who is supplying it? The inverter part. And how he is supplying? There is some controller sitting inside the inverter. There is a controller which sits inside the inverter that tells this is the time at which you have to send this much current and this much voltage, right? So question is how it is determined and how to design an inverter, especially for an EV application. This is not a very deep topic, but I'll just go cover it on a area wherever. So when you look at the inverter, I told this is how an inverter of a Toyota Prius will look like. And from the inverter, your power goes to which component? Yesterday I asked the same question, I believe. Where it goes? It gets connected to so in the motor, if you remember, there was a 3-phase terminal was there. That's where it is going to get connected, right? And when you open the inverter, this is what sitting inside. So one of the main component of the inverter is the power electronics device. Means what? Switches. So if you remember the image which I was showing in the BLDC, this image, this one. These are the 6 switches, 1, 2, 3, 4, 5, 6. So to operate a 3-phase motor, I need to have 6 switches. Clear? To operate one 3-phase motor, I need to have 6 switches. So in this case, for example, in Toyota Prius, I told 2 motors are there. So to operate 2 motors, 2 into 6, 12 IGBTs or MOSFETs, whatever it may be, will be used as the switching device, right? So the motor, this switching device has to open, close the switch depending upon the signal provided by the controller, right? That is the job of these power devices. So basically, when you open this inverter, we see that these are the power switches. You can see the IGBTs. These are the IGBTs for the motor, 2 motors. And in addition to that, your inverter also has certain sensors inside the inverter. Say when we talk about the inverter component, we have very important thing is the sensor modules. You have sensors, current sensors, you have temperature sensors, and you have the voltage sensing equipments as well. Why we need current sensors? Quickly answer, please. Why we need current sensors modules inside the IGBT, inside the inverter? Actually, what is the function this inverter is doing? It takes the input from the battery and it converts your DC input from the battery into AC current, AC output, right? So when doing so, the inverter wants to know how much current is coming inside the inverter, how much current is going out of the inverter. Is it required or not? Will you allow someone without asking into your home, to your home, right? We cannot allow. So basically, when an inverter operates, the inverter wants to know how much current is coming in from the battery and how much current is coming out to the motor. So we have a separate current sensing modules, voltage sensing modules, and it also has the control part where you have the the control strategy being implemented. That is what we are going to discuss in the coming slides. So what happens is it measures the current and temperature and the voltage, monitors all the aspects and makes sure that that inverter is working in the safe operating region. If the temperatures are not sensed properly, what will happen is it will directly damage the IGBTs. You know, IGBTs, these are all very sophisticated components. So the IGBTs have to be properly selected and sized. If you wrongly select IGBT switching device for an application without knowing what is the current capability it should handle, right? It will be very problematic. I should not take an IGBT which is used in a two-wheeler and put it in a car. Will it work? Or if I take an MOSFET or IGBT working in a car, if I put it in a two-wheeler, both are wrong, right? Both are wrong. So I have to properly size the IGBT inside an inverter. The main component is your power switching device. So I have to size the IGBT rightly for the right application. So if your electric vehicle is demanding very high torque, it's a high torque demanding vehicle, then obviously the IGBTs what you are using, the switches what we are using should be able to withstand higher current capability, right? Because when I put high current, the temperature of the IGBTs, the temperature of the switching devices will increase, which in turn will damage your performance. So because of that, you need to be very careful when selecting and sizing the power devices. And that is where I told selection of power devices is based upon the total voltage rating. And the criteria is that the voltage rating of the power devices, the switching devices, is at least twice the nominal battery voltage. What it means? If you are having an electric vehicle and that electric vehicle is having a battery pack of 200 voltage nominal capacity, then the power device what you are selecting, the IGBT or MOSFET, whatever it may be, either silicon based or other material based IGBTs or MOSFETs, the device, the switching device should be able to withstand minimum 2 times this voltage. What I mean is 2 times the battery voltage. So if the battery voltage is 200 voltage, what is the voltage to be minimum it should withstand? The power devices 400. Yes. So that is the minimum criteria that they should have when we are selecting the IGBTs and the MOSFETs for inverter application. So the current rating, not only the voltage rating, even the current rating should be large enough that there is no need to connect several. Say, what happens is, like when I select an IGBT for the inverter application, I should make sure that it will be able to withstand more current. And to withstand more current, what it means, it will get, when I supply huge current to IGBT, it will get heated up. Correct? When I supply huge current to the inverter, what will happen? It will get heated up. Means what? The IGBT will get heated up more. So the IGBT should have the ability to withstand higher temperature. That is what I call it as current rating. So more current rating means more ability to withstand higher temperature. That is why we use silicon carbide there. At the same time, not only this, the switching speed, how quickly I am able to switch the motor, switch from one phase to other phase, right? Switch this operation of the switches, how quickly it is happening, that is very important. In that perspective, yes, IGBTs have to be very quick. And look at this picture, how Toyota has developed its IGBTs from generation to generation. So 2004, when they started this Toyota Prius vehicle, at that time, the IGBT technology was different. And now they are into like 5th, 6th generation, Toyota Prius. So every year, what Toyota is doing, every year, the size of the IGBT has been reduced. Not only the size, the losses are also been reduced. Every generation, they are reducing the losses. At the same time, IGBTs operation, I believe, if you are from electrical background. So IGBTs, they open and close the switches basically for the power devices. And when they open and close, what happens is there is a breakdown voltage that will generate. So the breakdown voltage has to be higher and higher, very much higher. More and more the breakdown voltage is higher, the overall efficiency of this power device will be more. So what Toyota has done, every generation they have increased the breakdown voltage of the IGBT step by step. And the latest generation, the previous generation, they have achieved very high level of breakdown voltage. So what happens is every generation they are reducing the size of the IGBT and they are increasing the power density of the IGBT. And when you talk about the control technique, here also one simple thing. I told one component is almost common for all the motors. What is that? I told stator is almost same for all the motor. Similarly, the control technique also has been made common for almost all the motors with few differences. So today I am just going to explain you one of the control technique which is used for induction motors, PMSM motors, and your SYNR motors as well, synchronous reluctance motors. Right? All the motors are using the same control technique. That is what we are going to discuss now. So when you talk about the motor control, to run a motor, basically what you need current. The current is given because we need to produce torque. So based upon how much torque you want the motor to produce, you supply the current, right or not? Depending upon how much torque you want, you decide the amount of current, right? So depending upon how much current you want to supply, that is what the motor performance is based on. So when you look at the powertrain controller, this is an example of a powertrain controller. A powertrain controller, in order to give an output called a motor torque command. This is the command that comes into your inverter. This is the command that comes into your inverter. This is the command that drives your switches, basically. How this command is generated. To generate this command, what are all the inputs needed to the controller? You can see that to determine how much torque that the motor should deliver, the controller needs this information. One is the acceleration command. That means your accelerator pedal, how much accelerator pedal is being pressed by the driver, whether it is 10% pressed, 20% pressed, 30% or 50%, 100%. So what is the accelerator command pressed by the driver? And what is meant by deceleration command? What does it mean by? So whether the driver has applied brake or not. If he has applied brake, how much percentage of the brake has been applied? 10%, 20%, 50%. So the brake command is coming from the deceleration command, and the acceleration command is coming from the accelerator pedal, and the vehicle speed feedback, where it is coming from. So we have some wheel speed sensors on all our 4 wheels, and these wheel speed sensors determine the vehicle speed at any point of time, and that is also an important input to the motor controller. And what else you need? Is that is enough? No, not enough. You need to know the motor speed as well. Currently, what is the motor speed? Either the motor is running or not. So how to determine the motor speed? You know, using the sensors, right? And other than all these factors, you need very importantly the 3 factors, 3 parameters: battery state of charge, battery power, battery current. Without, say, end of the day, who is giving you the power actually to the controller, to the inverter? So without asking the battery whether you are having enough power or not, whether you can decide the torque that can be delivered to the motor, not possible. No. So definitely you need the input from the motor, so battery side. So the input from the battery is the battery state of charge, the battery's power, available power, and battery's available current capability. Say if your battery is completely drained, say for example, your battery is like only 10% remaining, 20% only remaining. Now what do you think? Whether your vehicle will perform at its fullest level? Is it possible? It will not. If it performs, then the battery will get damaged or it will get repaired. So what happens is the controller makes sure that the battery's power and the current is sufficient enough to determine the torque which is required at any point of time. Battery current which is available in the battery has to be taken, and that battery power has to be compared with the upper threshold, lower threshold. Battery current will be compared with the upper threshold and lower threshold. You determine that yes, the battery is having enough charge, state of charge. Based on all these parameters only, the controller decides whether the motor can provide a torque or not. Correct? And now how is the control strategy works? So based on this controller output, so end of the day, the controller determines what is the torque required by the vehicle. Or basically what happens is the controller translates the language. So the driver is giving the controller an information in terms of accelerator command, and the controller converts that input into torque command, right? So end of the day, the driver wants to give some torque, generate some torque only, right? When I'm pressing the accelerator, why I press the accelerator? Because I want to move the vehicle, so I need to develop a torque. So this controller translates that accelerator command input into a torque command, sir, actually, right? So when we look at that, how it is transferring, how the controller transfers the accelerator command of a driver into a torque command of the driver. Let's discuss about it. Here in electric vehicle application, there are generally in motors, there are so many control techniques are there. Whereas in electric vehicle, we use this control technique called as field oriented control. And modernly, very recently, we started using the field oriented control with MTPA. MTPA means maximum torque per ampere. Maximum torque per ampere control technique. So when you look at field oriented control, let me try to explain you it as simple as possible for me. I'll try to explain it to you in a very simple language, much possible. Okay. What happens is you have a battery pack in our car and you have a motor. So between your battery pack supplies the power to the inverter, and the inverter converts your DC power into AC and supplies to your motor. Is it clear for all the participants? I hope it should be clear. This point. This is a very, very complicated part. It may not be very easily understandable at the first moment. So step by step on this. So initially what is happening? The inverter takes the DC power from the battery. It converts the DC power into AC power output from the inverter. So your motor is supplied with a three-phase AC input called IA, IB, IC. So I supply a three-phase IA, IB, IC into the motor. And what happens is when my IA, IB, IC goes inside, now I have to control my motor. So when I have to, if I want to generate torque, what I have to supply? To generate torque to a motor, from a motor, what I have to supply? So whether if I supply a very constant current always, whether my torque will change? No. So in order to increase my torque, in order to develop more torque, I have to change my current accordingly, right? That is the motto. So what happens is, if you look at the previous picture that we were discussing, we are giving an accelerator command and the powertrain controller determines the torque command, right? Torque command. And that torque command means what? What is that torque command means? What do people think? What is meant by the torque command from the controller? So how much torque command is nothing but that it is nothing but the current. So what happens? The controller has something called as a lookup table. Where do you get the value of current for this particular torque? Where do you get it? Do you remember some graph that I have shown you yesterday? So we were talking about some graph, some particular graph, the efficiency maps. Do you remember the efficiency maps? So the efficiency maps are basically, they talk about the torque and speed of the motor, right? They talk about the torque and speed of the motor. Similarly, there is a table that we develop. We call it as lookup table, and that lookup table contains what is that torque developed by a motor for a particular current. 1, 2, 3, 4, 5, 6. Say for example, if the torque is 10 Newton meter, for 10 Newton meter, what is the current? 11 Newton meter, what is the current? 12 Newton meter, what is the current? So till what is the total maximum torque produced by the motor, there will be an current, specified current for it. Do you agree this or not? If you have a controller, what happens is the controller wants to know when the driver presses the accelerator, the controller understands this is the torque required by the driver. And now what the controller is doing? Controller goes inside the lookup table. It goes inside the lookup table and it searches for what is the current. What is the current? But it will not easily, you cannot get the current very easily, like I am telling here. So there are a lot of things happening behind. So the controller wants to search what is the current exactly required to run the motor at this particular torque. How it is determined? Let us understand that. So when you open a field-oriented control, this is what it looks like. Initially, it looks like a terrible diagram. I can understand your mind reading, guys, but I will make it more simpler. Just follow me up. So when you take a motor controller, here is where your motor controller comes into picture. So your motor controller takes the inputs, whatever I told you, only few have been mentioned here, and based on the input, the controller determines what is the demanded torque. Demanded torque, T, the tau. And based on the demanded torque value and the angular speed, torque speed, what you will come to know with this? Torque and the speed value. Speed value I am measuring with a sensor. So I am getting that here. What I will get if I have, so you know the torque speed characteristic of a motor, correct? So from the torque speed characteristic of the motor, I know that where the efficiency of the motor is very, very higher. And at the same time, I will also know what is the current at that point of time. So basically, I generate the reference currents. I generate some reference current based on this controller value. And what happens is now I have to calculate, I have to consider that whether the reference current calculated by the controller and the current which is supplied to the controller already are matching or not. So now what I'm doing is I am going into the motor. I am taking the three-phase current IA, IB, IC, which I already supplying to the motor. Guys, understand that I am taking the current values which is already going into the motor. Now what happens is, see these especially the PMSM motors, induction motors, all these motors are using the field-oriented control, because the field-oriented control basically operates the motor, considers the motor, either it is an induction motor or PMSM or any type of motor, it considers it as a separately excited DC motor. I hope you people know what is separately excited DC motor. So in separately excited DC motor, we control only two things: flux producing current, torque producing current. So you have the two currents which is flowing there. So we call it as flux producing current and torque producing current. So what happens in FOC, in the field oriented control, we are converting the PMSM motor into a separately excited DC motor. So for that, what we need to do, we need to have transformations. We need to use mathematical transformations. So you students would have studied many mathematical transformations. For example, Fourier transformation, Laplace transformation, right? Have you all studied these transformations in your mathematics? Yes. So you might have studied without knowing where it is being used. Maybe, I don't know. It depends upon who taught you, right? So if you know where is the application, that is very, very important. You should know. So here, what I am doing, here I am using some mathematical transformations in order to determine what is the right amount of current I have to supply for the motor for the demanded current, demanded torque. So what I am doing is, initially first task is I am using the forward Clark transformation. Forward Clark transformation. I am typing that in the chat box also for your understanding. Forward Clark, CLARKE, forward Clark transformation. The forward Clark transformation is used initially. So what they are doing initially? They are converting the three-phase current IA, IB, IC, because three-phase current is what going inside my motor. So I am taking the three-phase current and I am converting that into a two-phase orthogonal current, ID and IQ. Sometimes people call it as I alpha and I beta. I convert the three-phase current into two-phase orthogonal current to make it more simpler for my control. Otherwise, what will happen if I don't convert into two-phase orthogonal AC? What will happen is, say for example, if I have three IA, IB, IC in the PID controller, PI, for example, if I use a PI controller to determine the reference torque, I have to use three PI controller. One PI controller for IA, one PI controller for IB, and one PI controller for IC. So to reduce one of the controller, to reduce the usage of one of the controller on the PI controller, so people went for conversion of this three-phase machine into a two-phase. You can say in order to convert into a separately excited DC machine where you have only two current, ID and IQ. So ID is the direct axis current and IQ is the quadrature axis current, we call it as. So after this is what we call it as forward Clark transformation. And now what happens? My ID and IQ value is there. Now I want to know, I want to give it to the control part. I want to compare it with the control part. But still there is a now problem. What is the problem? Let's look at this picture. What is this? This is a merry-go-round. And imagine now you are standing on ground. And now you want to, this green color girl is your very close friend. Right? So you want to continuously see where is she in this merry-go-round. This merry-go-round is continuously keep on rotating. Right? And you are standing in the ground. Imagine that This is the rotating frame. This is the stationary frame. So now in a motor, which is the rotating frame? Which is the stationary frame? Which component is rotating and which component is stationary? Can you imagine in a motor? Can you imagine, guys, which is rotating in a motor? Motor is rotating and your stator is stationary. So what this picture means, what is the picture means? If I am determining the position of the rotor in the state, sitting inside the stator, is it like the same? Will I be able to catch the position of this green girl easily? Is it easily possible? And imagine that now the speed of this merry-go-round is increasing. And if the merry-go-round speed is increasing, what will be the difficulty of me to catch the green girl? Will it grow higher or lesser? Will my difficulty increase or not? So my difficulty to determine the position of my green girl will increase. Now what if the situation is like this? Where does the boy went? So currently the boy went on to the what he has done now? Can you people tell me what he has done now? The boy is now on the merry-go-round itself. So he is now rotating with the green girl itself. So what happens here? The difficulty on determining the position of the green girl becomes lesser, reduced. I can directly tell where is the green girl because I am also there, jumped into the rotating frame. Similarly, if I determine the position of the rotor or the rotor flux sitting inside the stator, it is not possible. So I have to transfer the current values from ID, IQ values from, this is the current value which I am getting it from the stationary frame. The controller wants to know what is the current in the rotational frame. So I have to convert the current value from stationary frame into rotational frame, for which I am using a transformation called forward Park transformation. Forward Park, P-A-R-K, Park transformation. So using the forward Park transformation, basically it is a mathematical equation, guys. Just two equations are there. I have not shown all the equations and all, but you understand that there is two equations. Okay, there is in this case there are three equations. One equation is for IA. If you substitute IA, you will get one equation is for IB. That means one equation is for IQ and one equation is for ID. So using the formula values of IA, IB, IC, if you substitute that in the equation, you will determine the IQ ID. And if you have the value of IQ ID, say for example I alpha and I beta, you substitute that in this equations. Two equations will be there that converts your current value from stationary frame to rotational frame. Called, what is the transformation? What is the name of the transformation used here? Forward Clark transformation is used in the first step. To convert your three-phase current into a two-phase orthogonal AC current, we use the forward Clark transformation. And after converting into two-phase orthogonal, I have to convert that from a stationary reference frame into rotational reference frame, for which I am using the forward Park transformation. Now it is very, very clear. I am getting a current value that is required for my controller. Now you know PI controller basically. You know PI controller, proportional integration. You can see this controllers. Basically, we use it in the control systems. So this PI controller needs the input. This is the input signal, and this is the reference input. The reference is coming from driver. The driver is pressing some accelerator, right? So based on that, the controller determines what is the current he is expecting, and that is compared with the current which is coming from the motor. Both these currents are compared and there is an error signal generated. And from the error signal, it goes to one more PI controller, and based on the error signal, the controller determines what is the actual power, actual current that has to be supplied to the vehicle or to the motor. So what happens is now the controller determines what is the current that I have to supply the controller. Now the problem is it is in the rotational frame. It is in the rotational frame. Now tell me what we have to do. I hope people can understand this. That means the people can explain the remaining part very easily. Correct. Very good. So I have to convert from rotational frame into stationary frame. So I convert the IQ ID from rotational frame into stationary frame. And then what I am doing now? what I'm doing now, I am converting, I have to supply motor with 3 phase, right? IA, IB, IC, but I have only IQ and ID. So I have to convert this 2 phase orthogonal phase current IQ, ID into once again into the IA, IB, IC value, and I have to give this input to the converter, the inverter part. Who is doing this job? So who was used there in the prior area to convert the 3 phase current into 2 phase current? Who was used? Forward Clark. Here I'm using inverse Clark. That's it. And previously I'm using to convert the stationary frame into rotative frame. I use the forward Park transformation. So here what I'm going to do, I'm using a inverse Park transformation. That's it. So I'm using an inverse Park transformation equation and converting the current. I'm determining the what is the current value in the stationary frame and converting that current value into a 3-phase current using the inverse Clark transformation. So this is how your FOC control works. This is how your controller determines what is the current that I have to supply for the motor at every millisecond. Every millisecond, this is happening in your controller. I hope you guys could little bit understand it. This is not so easy to understand for beginners. Yes, I believe understand that, but make sure that you repeatedly use when I am giving the recording to you, you repeatedly watch this information what I told you, because I cannot repeat it again and again. It's a big story here, right? You repeat this recording once again and again if you are not completely understanding it. Okay. So basically, understand that the controller uses majorly 4 mathematical transformations: forward Clark, forward Park, and reverse Park and reverse Clark. So using the 4 mathematical transformations, the controller determines what is the exact current that the motor has to be provided. So now after the transformation, the motor gives the IA, IB, IC value based on which you determine the switch signals, which switch should open. And based on which, once again, the feedback is received, once again calculate, once again run the motor, once again feedback. This cycle keeps on continuously running when you are operating the motor. And very important thing which I missed is to get the mathematical transformation, the Park transformation, very important value is the rotor flux angle. So that is why we call it as sensor based FOC, sensor-less FOC. So sensor based FOC is what most widely used in electric vehicle application. So we have a sensor that determines the position of your rotor flux, and based on the sensor information, you will have a lookup table inside this forward Park transformation. Inside this, there will be a lookup table. That lookup table will tell you what is the sin theta and what is the cos theta position. It's a quite deeper thing that the students may not clearly understand, but maybe faculties can understand it. So you will determine the sin theta and cos theta value from the lookup table, and that is where your ID and IQ values are determined. So basically understand, guys, that the motor control is not so easy in an electric vehicle. It is not so easy like your industrial application. In industrial application, we call it as triple VF. What is it? What is meant by triple VF? So in our general electric industrial application, we use this variable voltage, variable frequency type of control, which is not suitable for electric vehicle application, because electric vehicles have dynamic response. They expect dynamic response. That dynamic response is not possible with triple VF. So that dynamic response is possible with the controls like FOC and FOC maximum per ampere controls. So end of the day, the final summary is when you compare all these motors, induction, the permanent magnet motor, synchronous reluctance motor, induction motor, and the switched reluctance motor, end of the day, if you compare all these motors, this is what you see. In terms of power density, you have the PMSM motors having the advantage. In terms of operation efficiency, yes, PMSM motors are advantage. In terms of park load efficiency, who is better? I told. Do you remember? Park load efficiency. Induction motor. So induction motor has the most advantage compared to the PMSM. And in terms of constant power region, yes, PMSM motors have the wide constant power region. And in terms of cost, yes, synchronous reluctance motors are the cheapest motors compared to induction motor and the PMSM motor. Acoustic, rotor position sensing, all this perspective you have to compare. When sizing a motor, we have to compare all this perspective. And because of that, all this perspective right now, you see the PMSM motor has more advantages compared to the induction motor, and because of that, it is ruling the passenger car market. And right now, as I told, synchronous reluctance motor has only few disadvantages. That is what those disadvantages were being recovered by Tesla using the permanent magnet assistance. So finally, let's understand, let's match the motor for suitable applications. Now, can you people tell the motor suitable for two-wheeler motor? Which is the motor suitable for two-wheeler motors? Two-wheelers? Right now, the most suitable candidate for two-wheeler application is the BLDC, either hub motor, depending upon either it is a scooter or a bike. And but if you say some companies still use PMSM motor depending upon their performance requirements. And when you talk about two-wheelers will range from 250 watt to 6 kilowatt. And talk about three-wheeler. When you talk about three-wheelers also right now, BLDC and induction motors are the most widely used ones. And the range of the power will be like 3 kilowatt to 10 kilowatt. Not only passenger three-wheeler, like even the loader auto and loader passenger vehicles also. And when you go to the passenger car market, the range power requirement will be like 30 kilowatt to 400 kilowatt. And the most suitable motor is what? Passenger car market, most suitable motor right now at this point of time, permanent magnet synchronous motor, and next to that you have the induction motor, and next to that you have the synchronous reluctance motor. And in terms of trucks and buses, the last point is the trucks and buses. You have the induction motor, which can give more advantage compared to the PMSM. So they are the most suitable motor for heavy applications, and then you have the PMSM motor.